I wanted to go over a couple of t-test problems with you in preparation for your upcoming exam. The first problem is a problem I made up using the Barbara Helm dataset. In this problem, you're interested in determining whether male students sentence Barbara Helm to a different prison term than all the students who participated in the study as a whole. The mean prison term for everyone who participated was 4.8. Are the sentences given by men significantly different than those given by the population as a whole at alpha equals 0.05? Okay, so we drew a sample, or I drew a sample of prison sentences for men. Those prison sentences are given in this column over here. And you can see down here is the mean sentence that men gave. This column over here shows us we're using this column over here to calculate our sum of squares. Of course, to get a sum of squares, we simply take each individual observation and subtract the mean, square the difference, and that's how we get all of these guys over here. And we have a sum of squares of 23.71. All right. So what else do we know? Well, we know that n equals 7. Got 7 cases. If n equals 7, then the degrees of freedom in the problem is 6. Let's write some other things down. We have a population mean, it's given in the problem, of 4.8. We've calculated the mean for men. I'm just going to note it with a little m over there, but I probably won't follow through with that through the rest of the problem. Okay, and that's what, and we also calculated here the sum of squares for men, 23.71. All right, so what do we do now? Well, we're going to calculate a t-statistic. First question. Is this problem a single sample that we're comparing to a population mean? Do we have two independent samples, two samples of different people that we're comparing? Or do we have a problem where we have two means but drawn from the same group of people, the same sample with two different treatments that we're comparing? I think it looks like it's the first example. We have a population mean and we have a sample mean. So I think that's the kind of test that we're going to do. And the correct formula for that one is x bar minus samples, the mean for the population, divided by the standard error. All right, so do we have that standard error? No, we don't. It's not given in the problem. The standard error in a problem like this one is computed by taking the standard deviation and dividing by the square root of the sample size. Do we have the standard deviation? No, we don't. How do we calculate a standard deviation? A standard deviation is equal to the square root of the sum of squares divided by n minus 1. Okay, so we know now how to get s because we calculated a sum of squares. So at this point, it just becomes a question of plugging in some numbers. So let me start. I'm going to kind of work this. in an unusual way. We'll see if it works out. We have a sum of squares. Oops. We have a sum of squares equals 23.71. And we're going to divide that by n minus 1, which is 6, and take the square root. And that is going to equal 1.99 after we're all said and done. Okay? I'm going to take that 1.99 and we're going to plug it into our sample, our standard error formula. And we're going to get 199 divided by the square root of 7. 199 divided by the square root of 7 is going to equal 0.75. And I've been saying 199, you can see it's 1.99. It's going to give us 0.75. All right. So we now have our standard error, and we can go ahead and solve the problem. We have 6.4 minus 4.8 divided by 0.75. And we do that little bit of math over there. And that's going to give us 2.12 or 2.13 if you're rounding it out properly. So that is our value for t. That's our value for t. Okay, now we have to find the critical value for t. And we write that down as follows. We're going to write critical value for t at 6 degrees of freedom. We have n minus 1 degrees of freedom. There are 7 cases, so n minus 1 is 6. For alpha equals 0.05 equals 2.447. So our calculated value over here was 2.13. The critical value that we needed was this one over here, 2.44. Turns out that our calculated value, 2.13, is less than our critical value. So for this problem, we would fail to reject. And it looks like even though there are some differences here, there was sufficient variability. The sample size was probably the reason was the sample size was so tiny. We were unable to reject the null hypothesis. Okay, let's take a look at a different problem now. This problem has to do, it's kind of an interesting problem. Let's read it together. Research indicates that the color red increases men's attractiveness to women. In the original study, men were shown women's photographs presented either on a red or a white background. Photographs presented on the red background were rated significantly more attractive than the same photographs mounted on a white background. In a similar study, the one quoted here, a researcher prepares a set of 30 women's photographs. Again, 15 are mounted on a white background, 15 on a red background. One picture is identified as a test photograph. We don't need to worry about that one. Each male participant looks through the entire set of photographs and rates the attractiveness of each woman on a 10-point scale. The following summarizes the rating of the test photographs for a sample of n equals 9 men. So just to explain this 4 over here, for example, that 4 over there, for example, indicates the average score for participant A for all the white background photographs. And this 7 over here represents the average score for that particular participant, participant A, on all of the red background photographs. All right. So question 1 is, what kind of t-test do we need to do for this problem? Do we have a single sample and we're comparing the sample mean to a population mean? Does not look like that. We do have a single sample, but there's no population mean in the problem. In fact, what we're doing here is we're doing a repeated measure study because the same men rated both the white background photos and the red background photos. And the idea is to compare their ratings across the two different types. Oftentimes, probably a bit more common, we do something, we compare the same group at 2 periods in time. In this case, we give the same, each person gets both conditions, and we're going to compare the results. All right. So what do we have and what do we need? Well, if we're making a comparison, then we are going to need some difference scores. We're going to need some difference scores. Let me paste in some computations that I did using Excel. For 7, okay, 6, 7, 6, 7, all right, that's the correct data set. These here are the difference scores, and these here are the each difference score minus the average difference score squared. Okay. Over here is the average difference score, and of course, we're expecting the sign really doesn't make any difference here. The mean is -3, but it doesn't make any difference. It's only -3 because we the order in which we did the problem. We did the white background minus the red background. We could have done it the other way around, and this would have turned out to be a positive 3. So that doesn't make any difference. These here are the squared differences for each score, and this here is our sum of squares. All right. What else do we have in the problem? Well, we are given that n equals 9. There were 9 men who participated in the study. That means the degrees of freedom in the study is equal to 8. Okay, we have the mean difference score, which we've computed, and I'm going to make it 3. It doesn't matter that in this case that it's negative 3, but I'm just going to make it 3 to make the final calculations a little bit easier. And we have, of course, our sum of squares, which equals 18. All right, what do we need to solve this problem? Well, let's look at the formula. It is our usual, well, it's not actually quite our usual formula. Take our mean difference, and we're going to divide by the standard error, the appropriately calculated standard error. All right, our mean difference is, our average mean difference is 3. So we have that. Do we have our standard error? No, we don't have a standard error here. The standard error is calculated by taking the standard deviation of the difference scores. I'll put a little d to indicate that, and dividing by the square root of the sample size. Do we have the standard deviation of the difference scores? No, we do not. The standard deviation of the difference scores is equal to the sum of squares of the difference scores divided by n minus 1, and we take the square root of that. Okay. Do we have the sum of squares of the difference scores? Yes, we do. Okay, so we're ready to go to work then. And just like I did the other one, we'll work this problem in that way. The first one is going to be 18 divided by n minus 1, and again is 9, so 18 divided by 8, square root of that, and that is going to equal 1.5 after you take the square root. Now we're going to substitute that 1.5 into our standard deviation, into our standard error formula. Square root of 9, and that is going to equal 0.05. So t, in turn, equals the mean difference of 10 that we, I'm sorry, that's not the mean difference of 10, the mean difference of 3 divided by our standard error of 5, and that is going to equal 6. Okay, so our t-value in this problem is 6. What's the critical t-value? Let's take a look. T at how many degrees of freedom? T at 8 degrees of freedom for alpha equals 0.05. And the critical value here is 3.355. The value we calculated over here was 6. 6 is greater than 3.355. So in this problem, we would reject the null hypothesis. it looks as if men really do prefer the lady in red. Okay, let's take a look at a study now that has to do with the impacts of watching television on high school performance. Here's the problem. Again, from the text, research suggests that a relationship exists between TV viewing habits of 5-year-old children and their future performance in high school. These researchers report that high school students who regularly watched Sesame Street as children had better grades in high school than their peers who did not. So we're interested in testing this phenomenon using a sample of 20 high school students. The researchers first surveyed the students' parents to obtain information on family TV viewing habits when the high school students were 5 years old. Based on the survey results, the researchers selected at random 2 groups of students. One had a history of watching Sesame Street, and N was 10 for the Sesame Street watching group, and another did not watch the program, and again, N was 10. So the average high school grades were recorded for each student, and the data is shown as follows. Okay, so first question is, what kind of a problem do we have here? There are 3 or 4 different types of problems, depending on how you count. Do we have a single sample that we are comparing to a known population mean? No, we don't. We have 2 samples, 2 separate samples. So this is not an example of a repeated measures t-test or repeated measures design. We have 2 separate groups. One watched Sesame Street, the other did not. All right. Conveniently here, the textbook authors have provided us with our sum of squares and our and means and ends, so we don't have quite as much work to do as we would normally have to do. Let's first start out by figuring out the critical value for t. The problem says, you can't see it here, but the problem here is asking us to compute, to test the statistical significance at alpha equals 0.01. All right. So the first thing we need to do, because it's a t-test, is figure out our degrees of freedom. In a test like this, the degrees of freedom is equal to n1 plus n2 minus 2, which in this case, for this example, is going to be equal to 18. Okay? So we go to our t-table, and we look up the critical value for t at alpha equals 0.01, and you will find that that value is 2.8. I'm going to make it 2.88. I'm going to round it just a bit. Okay? So now we're ready to get started. We'll write out the t equation, as I always like to do, so we know what we're doing. And we're going to divide that by, of course, the standard deviation for the sampling distribution, which is also called the standard error. And what do we need and what do we have? So clearly we have x bar 1, we have x bar 2. We're called m here in this problem. Again, by convention, I don't know why they call it m, but at any rate, I'm calling it x bar 1 minus x bar 2. We need a standard error. We don't have a standard error here. In order to compute a standard error, we need a pooled variance, because the standard error is equal to the square root of the pooled variance over the sample size. And we figured out the standard error. We figure out the standard error with this equation. Doesn't look like we have pooled variances though, so the next thing we need to do is see if we have what we need to figure out pooled variance. Pooled variance is equal to the sum of squares for the first sample plus the sum of squares for the second sample divided by the degrees of freedom for the first sample plus the degrees of freedom for the second sample. All right. Do we have this? Yes, we do. We have our sum of squares, so we can get started on the problem. Just want to point out again here that it's important to remember that when we do this division, we're doing this addition first in the numerator, then we're doing the addition in the denominator, and then we're doing the division after that. So typically what we have is something that looks like this over here, where we have these two fractions that we're adding together separately. In this case, we're adding numerators first, denominators, and then dividing. It's important to remember that. All right, let's take a look at what we have. We're going to have, let's see, 200 for the sum of squares for the first sample, plus 160, sum of squares for the second sample. And degrees of freedom for the two combined, we already computed that over here. That's 18. And this is going to give us pooled variance of 20 after we do the arithmetic. All right, if we have a pooled variance, now we're ready to go back up to computing a standard error. So we have 20 over 10 plus 20 over 10 square root, and that you'll find is going to be equal to 2. Now that we have the standard error, we can go back to our t formula, and we're going to have 93, our first mean, minus 85, our second mean, divided by 2, and that's going to give us a t value of 4. 4, of course, is greater than our critical value, so for this problem, we would reject the null hypothesis. And it looks as if Sesame Street impacts high school grades. Did you watch Sesame Street? I did.